okay, so now that the Jordan canonical form theorem is over, we will talk about bilinear forms. And as I said today, because the last time was such a long lecture, today will be a short one to make up. So bilinear forms, in fact, symmetric bilinear forms. So one thing to say here right away is that bilinear forms are in so like linear forms are the same as linear functionals are in bijection with row vectors, and similarly bilinear forms are in bijection with matrices. Okay, so as a result, and when we talk about symmetric matrices, so this is the result or the section that's going to talk about them. Eventually, we will later on see something when the ground field, this works over any field. And we will eventually talk about something where the ground field is real numbers, and then we can say sort of more. And that is called the spectral theorem, but we will get to that probably next week or at the most the week after that, which is, I'm guessing, the final week of the syllabus, right? So, okay, of the course. Okay, so yes, let's start with some definitions. So, V is a vector space. V is a vector space over F. Let's make it a pen. Okay, now a bilinear form is precisely just a map which we have seen. So a bilinear form. Let's see, is it's just a bilinear map which we have seen. I don't have space. Space is, I'll call it kappa. Okay. So kappa in bilin is literally a bilinear map. And the word form just means that the output, so bilinear maps from V cross W to Z. Right? For vector spaces, V, W, and Z. A form is when that Z is the ground field. So linear form, bilinear form, trilinear form, and so on. And then the bilinear form is symmetric. We say kappa is symmetric. Such a map or a form, kappa is symmetric if the, well, you can guess what it is, right? Kappa of xy equals kappa of yx, or V prime. If kappa of V prime equals kappa of V prime V for all V and V prime. Okay, so we will talk about bilinear forms and mostly about symmetric bilinear forms. And so first let's start with examples. So example, let's say over any field. Let's say, okay, so V is F to the N. Okay, and now let me fix a matrix. Fix a matrix. A in F to the N cross N. And define kappa A. So kappa subscript A is a bilinear, well, is a map like this that depends on the matrix A. So kappa A of V prime is defined to be V transpose A V prime. Maybe I should say XY. Fine, this is fine. Yeah? Or maybe I will say X and Y for fun, just so that you don't keep confusing between the V and the V prime. So X is the first argument, Y is the second. So X, Y. X transpose A, Y. So what is this? This is, you can expand and check. This is literally, it's a summation I and J, both go from 1 to N. X, I, A, I, J, Y, J. This is not, this is obviously easy to check by now. Okay, so that's the definition. So this is a bilinear form. Then kappa A is a bilinear form. You just have to check bilinearity, but that is sort of obvious from this expression. Okay? It's bilinear in X and Y. Okay. The remarkable thing is every bilinear form is essentially this one. Right? So I'm telling you one example. Basically, I'm telling you all examples. So in fact, every is essentially this. And that is what I will explain to you now. Lemma, and it's not even something profound, so I just call it a lemma. Okay, so let V be finite, of course, we want to be finite dimensional. Okay, so let's see. So yeah, say dimension of V equals n, which is finite, and let me fix any order basis. Okay, so I don't really care what basis. Let me fix any order basis, and B, V1, V2, Vn, B, and fix B an order basis of V. Okay. Then for every kappa, there exists a unique matrix. So again, not only are these all of them, they are uniquely such. So if kappa is a bilinear form, kappa V cross V to F is bilinear. Meaning is bilinear is the same as saying is a bilinear form. Right? Then there exists a unique A. F to the n cross n, a unique matrix such that kappa of x and y equals, so this is a scalar on the one side. On the other side, you can do something like this. Write down x in the coordinates of b, this b. Okay, write down y in coordinates of, right, and then take a transpose, multiply by a, and write down y in the coordinates of, this is function, yeah. B. But what is it? This is precisely kappa a of x in b and y. So that's the point. Is every kappa is the same as kappa a with respect to some. So fix any coordinate basis, fix any bilinear form, then you can always find a unique. Okay, and the proof is very easy. The proof is very simple. Let Aij. So we'll prove it both ways. So suppose there exists such a okay, let me prove existence first and then uniqueness. Let Aij. So you can guess what this is, right? This should be EI transpose matrix times EJ. Like what is EI in this coordinate basis? It is VI. So it's kappa of VI and VJ. Right? And then you literally write down bilinearity, right? So now if given x, which is the coordinate, instead of saying x is xi EI, I'm going to write it this basis. So it's summation xi VI and y equals summation yj vj. J equals 1 to n, I equals 1 to n. Right? What do we get? We get that now let's calculate kappa xy. Well, this is kappa of summation this thing, and then summation that thing. And kappa is bilinear, so of course I can take the summations outside. Sorry, so it is xi, and then you get kappa of vi vj, which is literally Aij, and then you get Yj. And that is exactly the RHS. It's exactly there. So existence is obvious. Uniqueness is equally obvious. These are just very standard things. How is uniqueness immediately obvious? Well, suppose there is any matrix such that, so let me call this equation star. Suppose A satisfies star. Say f to the n cross n. Let's say A prime satisfies star. I want to show that A prime equals A, where A is given by this matrix. Okay? Satisfies star. Then what do you do? Let's calculate what is the ijth entry, and the ijth entry is given by Ei transpose and Ej. So that means again by Vi. Then A prime Ij is kappa of Vi Vj. Maybe I'll put in the step in between if you want. It's Ei transpose A prime Ej. So what is Ei? Ei is exactly Vi in the basis B transpose, then A prime, then Vj in the basis B. But that is equal to kappa of Vi Vj, and that is exactly Aij. And so the matrix A and A prime are equal at every entry, and so you're done. Okay, so this is very simple. Okay, so first of all we have seen so far is in linear form you get this thing, right? Yes, I should probably ask you homework here. Yes. This is nice. A good question for your homework. That has to do with the symmetric part of this lemma. So we will get that. Basically, the same exact thing holds if you want your form to be symmetric, except in that case, you need to require that your characteristic is not 2. So, I mean, I will ask you in the question, in the homework. Okay, this is the bilinear form part of it. Now we come to okay, of course I should write down some notation. Then because there is a unique matrix, let me just define its definition. Define A B to be in this theorem, in the above section. In the above situation. If you have any bilinear form, any field, any ordered basis of the vector space, then for that bilinear form you have a unique matrix, so call that matrix kappa B, like the coordinate matrix of the bilinear form. Okay, great. So now the natural question is, suppose the question. The same kind of question. Suppose I have 2 different bases. I have the same bilinear form over the same vector space, but 2 different ordered bases. How are these 2 matrices related? Say kappa is a bilinear form by Lin with B prime dimensional, and B prime, script B prime are ordered bases. Ordered bases. How are the matrices this and this related? It's very natural to us, right? So because like we've seen that the characteristic polynomial is the same regardless of which basis you take. The minimal polynomial is the same. The eigenvalues are the same. So all these nice things happen. The rank is the same of a linear. That's why you can define the rank of a linear transformation because it's the same regardless of the basis. So the nullity is the same, obviously. So it's natural to ask, how are these two matrices? Right? So and the answer is they are not similar as one. Sorry, they're not conjugate, but they are something else. I don't know. They're associated. There's some strange name. So I won't even sort of write down the formal theorem, but I'll call it a claim. Okay, so let P belongs to F to the n cross n be the change of basis matrix between the two bases. Be the change of basis matrix this is where I always get confused with n. One has to make some choice. So P is the identity with respect to B and B prime. Take the identity linear transformation on V with respect to B and B prime. Okay. And now let's write down some calculations. So what does this mean? It means V prime J. If I take V prime J, this is summation Pij Bi. I goes from 1 to n. Of course, I'm assuming, so I didn't write down that these things are the V prime J's are the B prime and the Di's are the B. I'll write that down. Maybe I should first write that down. All I was saying was, so if V is B1, B2, Vn ordered basis, and B prime is B prime 1, B prime 2, B prime n, then the equation goes. Because it's the identity map, summation Pij B. Sorry, Bi. For okay, so this is what we have. Okay, so now it's okay, so that's what it is. Now here is the claim. Right, what was the question? The question was how are the matrices, the unique matrices of kappa with respect to B and kappa with respect to B prime related? Here is the answer. Kappa B prime is P. Let's see, P is B prime, so it should be P transpose. Normally, you remember you have P and B inverse. Here you have P and B transpose. That's the relation. But in particular, the nice thing about this relation is that I'm going to eventually talk about symmetric forms. And so if the matrix with respect to any one basis is symmetric, then the matrix with respect to any other basis is also symmetric. Because if A is a symmetric matrix, then P transpose AP is symmetric. Because you take the transpose, this goes the other side and becomes transpose. And so, okay, so that's the nice thing. So that's why, again, you can talk about a symmetric bilinear form regardless of which ordered basis you use. Because of this, let me give this a name, let me call it star star. So I'll make that remark when we get to symmetric forms, which is well, okay. I'm going to make the remark in 1 minute. So, oh God. No, I did not say that. So I'll make the remark after this proof. The proof is not very hard, but something has to be written down. Okay. Proof. So first of all, it's enough to check the ijth entry because so check the ijth entry on both sides. So the left hand side is kappa, or as we already saw from this proof, it is B prime I, B prime J. Okay, that's the ijth entry here because with respect to the basis. Now let me expand each of these guys using this. So V prime, I'll create some dummy variables. So kappa of, let's say, k from 1 to n, p. So let's say we have the, so it's ki, vk, and then summation L goes from 1 to n, p, L, j, p, L. Okay, great. That is the formula. Now it's bilinear, so I can expand this out. So it's double summation k, comma, L goes from 1 to n, p, ki, kappa of vk, vl, and then p, l, j. Okay? And now let's write this down more carefully. Well, in a slightly different way. K and L again go from 1 to n. Pki is the ikth entry of P transpose. This number here, this scalar here, is the, look at this matrix and look at the klth entry. And then this is precisely PLJ. Oops, I don't need this bracket here. I need just a parenthesis here. And when you have three matrices like this, and this is the formula, this is precisely the ijth entry of this matrix. And therefore you're done. So the ijth entry of the left hand side is the ijth entry of the right hand side. And that proves it. Okay, so that's the claim, that's therefore obvious. Okay, so now here are some corollaries of this claim and of the previous lemma. So corollary 1, say kappa is symmetric. Okay, as a bilinear, is asymmetric bilinear form, obviously. Oops. Let's say A equals. So first of all, suppose A in F to the n cross n is symmetric, meaning A equals A transpose. Then so is kappa A. This is a bilinear form with two arguments, and this is symmetric. Okay. Now this is conversely. Say kappa A is symmetric. So kappa is symmetric. There is no A. Then no matter which ordered basis you choose, you always get a symmetric matrix. Kappa B is symmetric as a matrix, is a symmetric matrix. Let's say A fine is a symmetric matrix here. Then the form is symmetric, and conversely, if the form is symmetric, this is a symmetric matrix. So that's why, as we said, bilinear forms are in bijection with matrices once you fix an ordered basis, while symmetric bilinear forms are in bijection with symmetric matrices. The symmetric matrix for all ordered bases. Okay, so that's the result. I will leave the proof to you guys, and you should check this. I'm not going to check this. I should write this down. Fine, okay. The next thing is I'm going to say we can talk about the rank of a bilinear form. And the reason we can talk about the rank, so this one does not really need the this one doesn't really need this identity, because you just take any ordered basis and work it out, and you can check that kappa vi vj is aij, kappa vj vi is aji, and because the matrix is symmetric, so kappa is symmetric, or conversely, because kappa is symmetric, the matrix is symmetric. That's easy. That's just the definitions. Okay. So maybe the proof is to check. Okay. The second one though is going to use this identity. Use this thing. Let's just keep this one because this is going to be useful. The point is now take any bilinear form, not just symmetric. Take any two different ordered bases, just like this. See here, I did not require that kappa was symmetric. So this is true for any bilinear form. So take any bilinear form, any two ordered bases of V, and then let us note the fact that because this matrix is invertible, the rank stays the same. Okay, I don't know if we talked about this earlier, but I don't think I'm going to prove. Yeah. So for all the way to let V be finite dimensional and kappa bilinear form. This is in the bilinear maps from V cross V to F. Okay. If B and B prime are two ordered bases, are any ordered bases of V, then the rank of, I should don't do the parentheses probably, the rank of kappa with respect to the basis V equals the rank. This is a matrix, right? And this is another matrix. And these ranks are equal, as a result of which, by star. The proof. And this is proof follows from star, double star. This. Because P is inverted, remember P is the identity matrix, so this is inverted. So you can find a linear isomorphism between the null spaces of these two matrices using this. And therefore the null spaces are isomorphic, so the nullities are equal, so the ranks are equal. Okay, that is one way to see it. But as a result, one can define. So thus given such a kappa, so given V and kappa and define the rank of kappa to be the rank of kappa with respect to any ordered basis. Yeah. 1 second. Yeah. 1 second. Yeah. So any ordered basis. I don't need this anymore. So given V and K as above, V is finite dimensional, so I have a finite basis and therefore a finite matrix. Okay, that's what it is. Okay, that is the definition of the rank. And now, okay, almost exactly on time. So, okay, so now here is the main theorem. We will prove the theorem and we will stop. So 1 hour lecture basically. Okay, great. So theorem. Now this is the theorem we want to prove. So I think it's only for symmetric Bilinear forms, but it's good to develop all the obviously the notation and some preliminary results. There really are no preliminary results. One is that for every bilinear form you get a matrix, and vice versa. And the other is that if you have two different bases, then this is how the matrices are created. That's it, nothing else. Now the theorem is that yeah, suppose B is finite dimensional again, and kappa is a symmetric bilinear form. So kappa is a symmetric bilinear form on B. Okay, then there exists the order. Okay, actually there are three parts. So fine. The first part is that it's characteristic. Yeah. So each part assumes more and more this time on the field. Okay, not on the form itself, but on the field. So the first part only assumes that the field is characteristic not. Okay. The second part assumes that the field is closed under taking square root and has characteristic not to. And the third part assumes, okay, not exactly the square root part, but the third part is slightly more general but than the first part, but not than the second part. It assumes that the field is the real numbers. So again, it has characteristic not to, but it has much more. Right? It's the real numbers, so we understand square roots and so on. So the second, okay, let me write this down. If and so since the characteristic part is common, I could have written it over here, but I'm going to keep writing assumptions on the field, so I thought I may as well write them together. In any case, I think this is taken from Hoffman and Kunz's book, and they write it together, so I'll stick to their convention. Okay, so if this is true, then there exists an ordered basis B of V, obviously, such that let's put that here. This remember the matrix of kappa is in fact diagonal. Okay, so this is the result that we are going to see for real numbers when f is R. And in f is R, what we say is if you have any symmetric bilinear form or symmetric matrix, then there exists an ordered basis with respect to which the coordinate matrix of that symmetric form or symmetric matrix is a diagonal matrix. That's called the spectral theorem. But so in fact, it holds not just for real numbers, it holds for any field of characteristic not true. But the point is, for real numbers, we won't just prove it for symmetric matrices. It also holds for sort of skew symmetric matrices, and more generally for all complex matrices that are normal. That is far, far bigger than just the class of real symmetric matrices. So that's why we will do that in a different, more general setting, that side. But if you just want to talk about symmetric matrices, then you don't need to work over real numbers. Any field of characteristic not true will work. This is really like the spectral theorem over a general field. Right? So, okay. Second, if characteristic of f is not true, there are these three statements that I said, and f is closed under taking square roots, meaning every element of f has a square root in f. This is not true for the real numbers, right? Because -1 does not have a square root. But if f does, so for example, this is true for the complex numbers, under taking square roots, then in fact ask for the diagonal matrix to be the identity matrix, I think. Well, sort of. Sorry. Again, then there is this ordered basis of B of V such that same thing. And now the matrix is going to be, as I said, for every non-zero diagonal entry here, I can take the square root and take it outside and give ones. So I get a bunch of ones, and then I get a bunch of zero diagonal entries, which I can't do anything about. That's zeros. And that's the answer. That's exactly how every matrix looks like with respect to some, every symmetric bilinear form looks like with respect to some order basis. Such that the kappa with respect to B equals the identity of R cross R 0, 0, 0. This must be n minus R cross n minus R. But n is the dimension of V, and R, of course, is the rank of the kappa. And the third part is if the field is a real line, then you can do, well, then you see you can't take all square roots. But what you can do is for the negative numbers, you can take the square root of their modulus. And so you can say, well, I get a bunch of ones for the positive diagonal entries, a bunch of zeros for the zero diagonal entries, and for the negative diagonal entries, what might you expect? You can pause the video for a couple of seconds. And for those of you who just want to enjoy the show, it is precisely minus ones, right? So you get ones, minus ones, and zeros. Sorry, I don't know what. Okay, so here we go. So I'll say that. And now I think I want to say something like S and R minus S or something like that. Yeah. This is ordered basis, the same. All of this. Identity of size S cross S minus identity of size R cross R minus S, and zeros for n minus R. And of course, all zeros. That's how it is. These are the three theorems. These are the three statements. Again, the rank is R and so on. So first of all, R is the rank of kappa, less equals n is the dimension of V. Right, so 0, less equals S, less equals R, R being the rank of the form, less equals n being the dimension. That is the claim. Okay, now I think to prove it, I will use a black pen. Okay. Let's prove this and let's stop. Okay, so proof. Should we do? Let's start with 1. I think 2 and 3 are. 3 is going to be 2 lines and 2 is going to be 4 lines. So the main part of it is to do. But then you can just take away the square root of the absolute values and cut it. Okay, so the proof is easy. First of all, the proof is by induction on the dimension. So proof is by induction. So if n equals 1, then every bilinear form is just a 1 cross 1 matrix, which is symmetric and scalar, and so on. And yeah, then the proof is easy. But also it's easy for n bigger than 1 if kappa is the 0 form. Easy if n is equal to 1, you can check for yourselves. Just for part 1, because every 1 cross 1 matrix is symmetric. It's not easy, really. It is trivial. N equals 1. Or if n bigger than 1, and this form, bilinear form, kappa is not identically 0. If kappa is identically 0, then regardless of the basis, the matrix is 0. 0 is a diagonal matrix. A 1 cross 1 matrix is diagonal. So these are obvious things. So for these, I don't even mention it. So now let's take the induction step. The base case is done. So now we may assume, first of all, that n is bigger equals 2, and that kappa is non-zero. Okay, so of course, yeah. So now you can assume these things. Okay, great. So yeah, the first claim is there is. So what does kappa mean? Non-zero mean, right? Let's see. So by the lemmas that we proved, so I should here. By the lemmas that we proved, if the matrix of kappa, if it's a fixed order basis, if the matrix kappa B is zero matrix, then kappa is identically zero. That is also clear from the lemmas and the proofs. So to say that the form is non-zero means the matrix is non-zero, means at least one entry is non-zero. Okay. That means some kappa of, so the kappa of Vi comma Vj is non-zero. What we want to prove is not that kappa of Vi comma Vj is non-zero. I want the same I and j. Now that may never happen. But what I want to prove is there is some vector V0, so that kappa V0 comma V0 is non-zero. Not Vi and Vj, which may be different, and then Vj and Vi, but it's symmetric. No. I want kappa of some vector and itself to be non-zero. So that's the first thing. Claim 1 maybe, or yeah, sure, no. Claim 1. There exists V0 in V such that kappa of V0 comma V0 V0 comma V0 is non-zero. The proof is, I think, by contradiction. It's something called the polarization identity. So the whole point is that the characteristic is not 2. So I'm going to use it very crucially to prove this. So what happens if every kappa of V0 comma V0 is 0? If every one of those is 0, then I claim that kappa is 0. And that's the problem, right? Indeed, if not, then kappa of V0, so let's say kappa of V comma V is 0 for all V in V. But then I'm going to calculate kappa of V comma W, V not equals W, anything, and prove that is 0. Let's see that. But then kappa of V comma W. Now here is the thing. Kappa of VW, think of it like it's a product. V times W. I know that all squares are 0. V times V is 0. So can you write down V times W only using squares? And the answer is actually yes. If the form is symmetric, then VW plus WV, 2VW, is V plus W square minus V square minus W square. And all squares are 0. Therefore, that difference is 0. So half of the difference is 0 because the characteristic is not 2. So I can divide by 2. And therefore, I'm done. Let me exactly write that out. So this is, look at kappa of V plus W. V plus W. So you have to basically work this out. You have to expand. So kappa V plus kappa W plus kappa VW plus kappa WV. And those last two cross terms are equal because kappa is symmetric. So if I just subtract the square terms, kappa VV and kappa WW, and divide by 2. Then this equation holds. This identity holds because two things. One is that the characteristic is not 2. So I can indeed divide by 2. This is like 2 inverse. I should not say half. That doesn't make sense in a general field. I should say 2 inverse. So again, but 2 doesn't make sense, but like 2 is like 1 plus 1. So 1 plus 1 inverse. And the second point is that kappa is symmetric. So when you take, when you expand this out by linearity, these two terms cancel out. You get kappa VW plus kappa WV. So kappa WV equals kappa VW plus kappa is symmetric. So these two are the reasons that equation holds. But now look at this. Suppose this is true for all vectors V. then that means this is 0, this is 0, this is 0. And this happens. So that means kappa VW is 0 for all vectors V and W. And that is a contradiction, right? We already said that we start with a kappa that's not 0. That was the point of finishing of the, oh god. My mistake. Very sorry. I kept writing, I wrote non-zero here, I kept saying if kappa is 0, it's trivial. Great. So now, because kappa is assumed to be non-zero, this is a contradiction. So, therefore, claim 1 is true. Maybe I should say 2. Because it took a little bit of work to prove it. This is the proof of claim 1. Now I write down claim 2. I need better pens. They all start very nicely and then they fade away very quickly. Anyway. Where is it? Okay, so that was claim 1. Just that there exists at least one vector. And now I look at what one calls the perp space, I think, to that vector. So what has happened here? Yeah. Oh, by the way, I should mention that this is called the loop, the polarization identity. So in any field of characteristic not 2, you have something called the polarization identity. This is just general knowledge. I won't ask you in an exam or something, but yeah, to express cross term as a difference of squares is polarization. And this is the quadratic version of it. There are higher order terms also. You can try to write down x, y, z as somehow differences of cubes and so on and so forth. We will see this principle twice more, once in real inner product spaces and once in complex inner product spaces. Okay, so we will get it. Most likely next week again. Okay, claim 2. So now let's define the perp space to be, I'll call it U apparently. Let V naught perp equals U be defined to be the set of all V in V such that kappa of V naught comma V is 0. No space to write these things. Let U equals V naught perp is defined to be the set of all V in V such that kappa of V comma V naught, kappa is symmetric, so I can write down either way. Okay, let U be this thing. The claim is that the dimension is n being the dimension of V. I claim that this is co-dimension 1 or dimension 7. Then okay, that's the thing. So proof this is not too hard again, but yeah. Okay. So the way one proof goes, I guess, is take a basis of U and expand to a basis of V. Or take a basis of U and say that adding V naught does the trick. So then say V1, VD, B, and ordered basis of U. I mean, I don't need the ordering, but fine. Let's just say an ordered basis of U. The claim is that then that plus V V0 through VD is a basis of V. And therefore we are done. Yeah, that's a thing. V0, V1, VD is a basis of V itself, of the full space. Okay, so why is that true? So you have to do two things, linear independence and spanning set. So let's do span first. Maybe I'll take this back now. Okay, so clear proof of span. Take any vector V in V. So given V in V, I want to write down V, and this is a principle that you will see next time for inner product spaces and orthogonal vectors. But I want to write down V as summation Ci Vi, where I goes from 0 to V now, because I want to prove it's a spanning set. So how do I do that? Well, what I do is I want to write down V, first of all, as a sum of something in U and a multiple of V naught. If I can write that down, then the multiple of V naught is multiple of V naught, and something in U, well, this is the basis, and so I'm done. Okay. So consider the following. Let U equals V minus, this is the principle I'm going to use in orthogonality and inner product space. V minus kappa V naught V by kappa V naught V naught. And you see, this denominator is why I require claim naught. This denominator is non-zero in the field, and therefore it makes sense to divide like this, multiply the V. Okay, so this is just literally something plus V plus some multiple of V naught. The claim is U is in capital U. And therefore V would be equal to something in capital U plus something times V naught, and I would be done. Okay. Claim or subclaim, because this is the claim, U in U. So this would imply that V equals U plus some alpha V naught, so alpha V naught, or C V naught, let's say, for this scalar C, minus kappa over kappa. Okay? And so the proof would, the spanning set is indeed span. By V naught to Vd. Right? So that is why we want to claim that U is in U. But that is very simple. How do you check U is in U? You just check that kappa of U comma V naught is 0, the definition. So proof, so check. Kappa of what you want to prove is in U and V naught. Well, kappa is bilinear, so well, I'll keep the V naughts fixed and I'll just do bilinear in the first coordinate. This kappa of V comma V naught, right? Minus that scalar. The scalar comes out because again bilinearity. V naught by kappa of V naught V naught. If you can't read it, I'm sorry. I'll see if I can do it better. Minus kappa over kappa V naught V naught V naught. Okay, that's the scalar coming out, and then there is the kappa of this vector and V naught. But this vector itself is V naught. So look, this number and this number are the same. So they cancel. Now this vector minus itself is 0. And that's why you're right. So that's the end of that proof that indeed U is in U because this calculation is true. Therefore V is in the span of U and V naught. So from V naught to Vd. And therefore it's indeed a spanning set. Every vector U is in the span. So every vector V is in the span. Okay, great. That's the spanning set. What about the linear independence? All this is the proof of part 1, okay, not of the part where the field is closed under square roots or the field is the real numbers. Okay, so linear independence. proof of independence. Fine. Okay. Well, linear independence is actually from a very, very old homework. Right? These guys are already linearly independent. This is this is a linearly independent set. This guy V0 is clearly not in the span. So we need to show that V0 is not in the span of these things, right? Yeah. So the claim is that V0 is not in the span. Let's write this down actually. Okay, maybe I should use a blue pen now because I'm sick of this constant. The claim is that V0 is not in the span. If you can prove this claim, then here is a linearly independent set. Here is a vector not in the span of them. When you add such a vector to the linearly independent set, you still get a linearly independent set. That's a very old homework, like homework 2 or something, extremely basic, which we kept using again and again in this finite dimensionality proof. Right? So this proves it. This proves linear independence by an old homework. And why is V0 not in the span? Because suppose proof. And this is also a claim, not a subclaim. No, this is a subclaim. This is a proof. If V0 is in the span, I goes from 1 to D now because V0 is 0 here, V0. Then, what is kappa of V0, V0? This is equal to kappa of, so I'll jump a step. Summation Ci kappa of Vi comma V0. Because right, I'm just expanding this one V0 I'm changing this way and using the linearity in the first coordinate to take the sum outside. But look, each Vi is a basis vector for U, so it's in U in the first place. It's an element of U. Therefore, kappa Vi comma V0 is 0. So this is summation Ci times 0. And that's a contradiction because we already know that kappa of V0 comma V0 is not 0. That was what we proved in claim 1. And therefore, this is a contradiction. So V0 cannot be. This contradiction meaning this if must be false. Okay, so now we have proved 2 claims. So we are just assuming that the field is characteristic not true. The form is the bilinear form is symmetric. Of course, induction, the bilinear form is not identically 0, the dimensions at least 2. And now what we have said is that there exists a V0 such that kappa V0 is non-zero. From that we deduce that this basis, this vector space, the first space is dimension n-1. Not only that, the ordered basis of this space extends to the basis of take any ordered basis, then you can extend it by just adding V0 to an ordered basis of V itself. But now here is the key point. The key point is this thing. It's a smaller dimensional space. We are doing induction of dimension. So by induction hypothesis, there is an ordered basis of this vector space with respect to which kappa is diagonal. Take that ordered basis to be V1 to Vd. And now attach V0 and check that you just get a diagonal matrix. Okay. So now back to the proof. Proof of part 1. And we are doing part 1 of the theorem. Okay, so we are still back at the induction step. So now, so because of this thing, by induction hypothesis, by the induction hypothesis, obviously, I'm not going to write that. There exists an ordered basis. Let's call it B equals V1, Vd. So Vn minus 1. Now D is n minus 1 of U. So the V0 already we chosen fixed. Okay, such that if I look at kappa on this subspace U, okay, let me call this B prime because I want to say that B is the basis for it. This is diagonal. Let's give, in fact, give these things names. Say, I should give them names, so let's say sigma 1. I won't call them lambdas, I'll call them sigmas. Because these are not eigenvalues. Okay, great. So that's what they are. Okay. Now add the V. So where do I want to add the V? I can add it in the beginning as usual. Let V be V0 and then V1 and then Vn minus 1. And let's calculate the matrix. So first of all, if I take the matrix is going to look like a big matrix, and everything except the first row and first column we already know. It's really what happens here and here. Well, here it is just kappa V0 comma V0, and this is some non-zero number. That's fine. Now here each of these is kappa of V0 comma Vi or kappa of Vi comma V0, and those guys are all 0 because this is Vi, the basis of the curve space. So you have a diagonal matrix here, zeros and 1, 1 and 2. And that's exactly right. Hence, sorry, not hence, then kappa equals this, and this is diagonal. That is the end of part 1 of the proof of the theorem. The proof of part 1 of the theorem. Okay. Once you find out that the curve space is n minus 1 dimensional, you can write down the diagonal matrix for it with respect to some basis. And now just calculate, and we check that with respect to the extra element V0, you get a diagonal matrix. This is part 1, and now part 2 is not too long, and part 3 is roughly the same thing. Okay, so part 2. So now we know that the field has characteristic not 2 and it is closed under taking square root. So by part 1, first of all, I get a diagonal matrix. Okay. So by part 1, there exists a basis. Let's call it B prime. Let's call it V1, VR plus 1, Vn. I'll call it this way, such that the matrix of kappa with respect to B prime is diagonal, but I'll call it sigma 1, sigma 2, sigma r, and then 0, 0, 0. Okay, where all the sigma i's are non-zero. No sigma I equals 0. None of them is 0, all of them are non-zero. Yeah? So R is the rank of the form basically, because the rank of this matrix is all non-zero numbers, and the rank of this matrix is R. And as I said, the rank is independent of which basis you choose. So now we have this basis for which the rank is R. So it's R for everything. Okay. Okay. No sigma I is 0. Now I just want to call a different basis with respect to which I can divide out by the square roots. Remember that the square roots of these guys are in the field. That's by the assumption. So now let's see, do I want the other way around or this way? Dividing by that. Let equals V1 by square root sigma 1, VR by square root sigma r, And then the rest of it, VR is not to be. This is my ordered basis, okay? You can check again that when kappa of, let's look at the ij factor, kappa B, this is a matrix. Okay. Well, if I is not equal to j, first of all, the case of off diagonal, then you have kappa of some v, scalar multiples of vi, and a scalar multiple of vj. So the scalars come out, and the remaining inside is kappa of vi comma vj. But kappa of vi comma vj is 0 because this is a diagonal matrix. Okay. And what about kappa ii? The diagonal matrix. Maybe I'll just do it. Yeah, I'll just say it this way. So first of all, if I is bigger than R, then my basis elements did not change. So kappa of v comma v is the same as the kappa here. So it is 0. But what happens if I is less than R? Then it is kappa of this comma itself. But then the scalar comes out outside, so you get kappa of v1 times 1 over square root sigma 1 times another 1 over square root sigma 1. Both of these from both arguments. So this 1 over square root sigma 1 square is 1 over sigma 1. The kappa of v1 comma v1 is sigma 1, so you get sigma 1 over sigma 1. So you get 1. And this, I will leave all this to you guys to check. And it's trivial to check because I'm giving you the equation for kappa of vi comma vj. That is this matrix. I'm saying now I'm calling v prime I is vi over square root sigma I, or v prime I is vi. This is trivial to check. Okay, so therefore, but that's it. But what does that mean? It means that this matrix kappa b is exactly a diagonal matrix first of all, and moreover, the diagonal matrix is the identity matrix followed by a 0. Okay, that was part 2. Part 3 is basically I won't write it, but it's exactly the same proof. First I will repeat this proof. So you get these numbers, but the only thing now is these numbers are possibly negative. I could have minus ones everywhere. These are just some real numbers. And now for negative numbers, I cannot take square roots of them in the real field. Remember here f is r. So what do? Very simple. I divide by the square roots of the absolute values. Don't divide by square root sigma I, divide by square root mod sigma I. Then you would get 1s if the sigma i's are positive and minus 1 if the sigma i's are negative. And that's exactly the formula. Repeat the same proof. But with dividing instead by rescaling the vi for 1 less equals I less equals r by 1 over the square root of mod sigma I, rather than instead of 1 over the square root of sigma, because the sigma is will be negative. Okay, and that's exactly the exact same proof works. You can check that you get some minus ones, some ones, some minus ones, and some zeros, and that's exactly the form of theorem part 3. Okay, so that's the end of this section. As I said, it was a short section. So next time onwards, we will start with inner product spaces. Okay, so now we finished the Jordan canonical form and the symmetric bilinear forms, and now we will go on to inner product spaces, where we will prove part 1, which was the spectral theorem, but in much more, so for a broader class of real and complex matrices, or normal matrices. Okay, that's it for today.